Hello everyone, my name is Neal and I'm a PhD candidate from the University of Michigan. And I'll be providing an overview of persistent memory research for this year's USENIX ATC and OSDI conferences. So what exactly is persistent memory? Well, to give a slightly obnoxious definition, persistent memory is just like regular main memory, but persistent. Specifically, persistent memory is a memory abstraction where memory retains its values without actively being powered. Persistent memory is actualized in a few different ways. The first way is through a system abstraction, such as a memory mapped I/O to files on block storage devices. The second method is through power backup. These kinds of persistent memory are volatile memories with built-in power supply, which is used if the rest of the system is no longer powered. For example, some DRAM modules employ supercapacitors to retain data for long enough to trickle unpersisted writes to flash storage. Finally, the last method is through inherent non-volatility. These are durable storage devices which can be accessed and modified in the same way as volatile DRAM. It's this latter category that people primarily focus on today, and this is the type of persistent memory that all of the papers in this year's conferences are discussing. To understand why modern persistent memory research is so focused on non-volatile memory, it would help if we could understand a bit of the history of persistent memory technologies. The first persistent memory technology, magnetic core memory, was actually the predominant form of random access memory in computer systems in general. This kind of memory worked by using electric current to magnetize these little ferrous toroids, and the cores would stay magnetized until acted on by some other electrical force. Coincidentally, these core memories are the origin of the core dump terminology, which you may have encountered before. These memories were fairly sparse and expensive to manufacture, so they were quickly replaced by volatile DRAM technologies when they became available. The first device that we see which is close to modern-day persistent memory would be EEPROM, or Electrically Erasable Programmable ROM. The technology behind EEPROM is the same as modern flash devices. However, EEPROMs offered much smaller erase units, as low as byte granularity, allowing reads and writes at memory addressable sizes. However, using EEPROM as a read and write medium is impractical as a general-purpose storage device, as the latencies between reads and writes are highly asymmetric, with writes being thousands of times slower than reads. The next notable persistent memory devices are battery-backed RAM technologies. These memories could retain data for years, like in the case of battery-backed SRAM contained in Game Boy cartridges. Unfortunately, large capacity devices typically draw more power than your typical coin batteries can supply for long, and so these memories are not a good solution for storing larger volumes of data. During this time period, we do see academic research on persistent memory systems, for example, on programming language abstractions, where persistent memory operations would be transformed into database transactions. However, these systems never saw serious adoption, as persistent memory programming wasn't practical from an efficiency standpoint. However, this started to change starting in the 1990s. One of the first modern persistent memory devices was ferroelectric RAM, which is constructed similarly to DRAM cells, but employs a ferroelectric material which is polarized on writes, keeping the memory persistent on power loss. We also see development of magnetoresistive RAM in the 2000s. In particular, spin-transfer torque MRAMs, which use spin-polarized currents to alter the state of nanometer-scale magnetic layers, were a massive improvement over older MRAMs like magnetic core memories. Both FERAM and MRAM are fast and have a high endurance compared to flash memory, but are nowhere near dense enough to compete with flash storage block devices. Even today, STT-SRAM devices are being produced at the scale of tens of megabytes per device, where modern SSDs are in the terabytes. And so even until this point in the timeline, block addressable flash memory has been the storage device of choice for practical reasons. However, it turns out that advances in phase change memory would quickly advance the field of persistent memory to where it is today. Phase change memory, or PCM, is actually fairly similar to CDs and DVDs, as they use the same kind of galcogenide glass crystals in their media. But in PCM, the glass is used to encode high and low resistance states through the crystal structure, rather than being examined for its optical properties. Now, the idea of PCM has been around since the 60s, but the recent innovations in production allowed this technology to really take over the persistent memory scene. In particular, manufacturers were able to produce stacked PCM cells, known as 3D crosspoint technology, which allowed for much higher densities than was feasible for either FERAM or STT-MRAM. So in 2015, Intel and Micron announced this new technology, And then in 2017, Intel was able to put this new technology, branded as Optane, into their new state-of-the-art NVMe SSDs, bringing fast random access to block storage devices. This was great and all, but it wasn't really the exciting bit. In 2019, more importantly, Intel released its first line of Optane-powered main memory modules, bringing fast, non-volatile main memory to market. So nowadays, when people talk about persistent memory or non-volatile memory or storage class memory, they're generally referring to Intel Optane memory. This is because Intel's production is the first practical persistent memory device to come to market, thus driving a lot of innovation both in industry and in academia. The first persistent memory that Intel released, the Series 100 persistent memory, offered read latencies between 2 and 3 times slower than DRAM, or around 300 nanoseconds per access. One of the notable considerations the developers had to account for when using Series 100 Optane memory is that updates had to be explicitly evicted from the volatile CPU cache. Otherwise, updates destined for persistent memory could remain in the CPU cache indefinitely and be lost on power failure. In 2020, Intel then released the Series 200 Optane memory. This memory, when used in conjunction with third-generation Xeon processors, provides a new feature called Extended Asynchronous DRAM Refresh, or EADR. EADR is aware of persistent updates in the CPU cache and includes the entire cache hierarchy in its power failure protection domain, simplifying the task of low-level persistent memory programming. In addition, the new series of Optane memory offers around 32% higher bandwidth than the Series 100 memory. So now that we live in this great time with all this nice persistent memory, how are people actually using it? For the rest of this preview session, I want to talk about 3 areas of research in the design of systems and tools which use persistent memory. The first is in the design of efficient persistent data structures and storage systems. The second is in the considerations of using non-volatile memory as volatile memory extensions rather than exclusively as a durable storage device. And the third is in the design of tools to make it easier for developers to design aforementioned data structures and systems. There are a number of interesting characteristics of persistent memory to consider when designing persistent data structures. First of all, as we discussed previously, persistent memory is not quite as fast as DRAM, but still has access performance far faster for small reads than SSDs, and so many persistent data structures are designed to be accessed and modified directly on persistent memory. This is unlike block storage devices, which usually require page caching in DRAM, requiring more block-centric designs. Persistent memory is also denser than DRAM. Intel sells Optane in 128, 256, and 512 GB form factors. This is denser than DRAM, but not as dense as SSDs or large hard disks, and so some trade-offs may need to be made based on the targeted dataset size. Another critical point to mention is that persistent memory has somewhat asymmetric access performance in comparison to DRAM, with random reads having almost twice the latency of sequential reads, as you can see in this graph, which compares 2 emulated persistent memory devices to Intel Optane's actual performance characteristics. Furthermore, persistent memory also has asymmetric read and write bandwidths, with both read and write bandwidth being lower than DRAM bandwidth. All in all, persistent memory is close to the performance of volatile memory. Legacy I/O stacks were designed for much slower block storage devices, which have a lot of overhead if they're instead used in conjunction with persistent memory. This is because relative to the performance of persistent memory, legacy software overhead is much higher, necessitating the design of systems specifically for persistent memory platforms. So the first paper in these conferences to address these problems is NAP, a black box approach to NUMA-aware persistent memory indices. NAP addresses a subtle issue in persistent memory programming. Memory accesses on a different node in a non-uniform memory access architecture, or a NUMA architecture, suffer from even lower memory bandwidth to remote nodes than to local nodes. Since persistent memory systems generally have persistent memory distributed across NUMA nodes, ensuring that persistent data is located on local memory nodes becomes an important task, as otherwise the system can become bottlenecked on remote memory accesses. So the authors present a NUMA-aware adaptation layer, which automatically makes concurrent persistent data structures NUMA-aware by locating hot accesses on local nodes to avoid remote NUMA accesses as much as possible. This paper ultimately addresses the importance of accounting for the location of persistent memory in the system, as this has a major impact on the performance of systems built on top of persistent memory modules. Another area of interest in persistent memory research is how to best use persistent memory in networked systems. In the paper characterizing and optimizing remote persistent memory with RDMA and NVM, the authors demonstrate how to optimize remote direct memory access systems, or RDMA systems, to efficiently use real persistent memory devices. The authors show that treating non-volatile memories in the same way as DRAM, prior RDMA work loses out on potential optimizations. By providing persistent memory-specific hints to systems, the authors demonstrate that persistent memory-enabled RDMA systems can have up to 2.4 times better performance than systems which are unaware of persistent memory. This paper really demonstrates the importance of evaluating systems on real hardware. Back in the early 2000s, before Optane memory was commercially available, many people did research on simulated persistent memory. While the results of these works may hold for real hardware, it's not guaranteed, as many simulators do not have the same performance characteristics of modern persistent memory hardware. The last paper in this area is on the design of persistent memory file systems. In the first responder paper, the authors argue that prior designs of persistent memory file systems have not leveraged the full power of persistent memory, and these works treat persistent memory as essentially a faster block storage device than really as a memory device. The key innovation behind the first responder paper is to leverage the power of persistent memory while leveraging the stability of existing file systems on block storage devices. First responder uses persistent memory to function as if it were a persistent buffer cache, serving hot data from persistent memory and spilling contents to mature legacy file systems when the capacity of persistent memory is exceeded. First responder is able to perform competitively with file systems which were created for persistent memory, such as Nova, without having to write a new file system from scratch. First responder shows how developers can use persistent memory to quickly accelerate a variety of systems, in this case unmodified legacy file systems, without having to perform a lot of code rewriting, which can be time-consuming and error-prone. Now I want to talk about using persistent memory devices as volatile memory. There are a number of advantages to using devices like Optane as simply a large pool of volatile memory, since it's denser than DRAM, requires less energy since they don't require DRAM refreshing, and they're much faster than swapping volatile memory to disk when DRAM reaches capacity. On the other hand, persistent memory is slower than DRAM and does have lower bandwidth than DRAM, hampering high-throughput workloads. These are trade-offs developers can consider when designing memory caching services, depending on their workload or specific service goal. For example, in this graph, while using Memcached or Redis with Optane is slower than using it with DRAM, these services can cache up to 8 times more objects than with DRAM alone. One paper in ATC analyzes the use of Optane as a volatile cache for large flash-based key value stores. In this work, the authors consider the challenges of servers with reduced DRAM capacity, as DRAM is expensive and consumes a lot of power. By equipping these servers with non-volatile memory, configured as a hierarchical cache for flash storage in conjunction with limited DRAM, the authors show that RocksDB can provide up to 80% higher throughput while reducing overall operating costs by almost 50%. This paper really demonstrates the utility of using non-volatile memories like Optane not only as a volatile memory device, but as a cost-saving one, as Optane is both cheaper per gigabyte of storage than DRAM and has lower overall operating costs. Finally, I'll discuss the challenges of persistent memory programming and why building tools for persistent memory system developers is also a hot research topic. In persistent memory systems, there are many crash states for developers to reason about. In this example persistent memory program, each store to persistent memory can create a brand new crash state with potentially different consequences with regard to data consistency. This means that developers have to reason about more update orderings than they might have had to on legacy systems. Furthermore, on Series 100 Optane memory, or on other systems which require explicit cache flushing, developers also have to ensure that CPU cache and flushing instructions are properly inserted into their program, which can be tedious and error-prone. This programming task is even more challenging when developers aim to port legacy applications to use persistent memory, as developers may need to consider all these crash points for codebases which may encompass millions of lines of code. They may also have to extensively modify these legacy systems to port them from using a file system API to using persistent memory. And they may also be porting volatile data structures to persistent memory with the intent of making them durable. And so they must consider cache consistency semantics for data structures which have always been volatile. All of these factors make persistent memory development challenging and potentially error-prone, to say the least. To help developers port volatile data structures to persistent memory, one group of researchers has developed Ayudante, which uses a reinforcement learning approach to help persistent memory developers. Ayudante uses a reinforcement learning pipeline to automatically generate persistent memory code and checks for volatile data structures, and then generates a report that developers can later use to further refine and optimize the automatically generated persistence code. Ayudante demonstrates that automated approaches are able to automate many of the tedious parts of persistent memory programming and can do its job as well as developers can. Along similar lines as Ayudante, we have TIPS, which provides a data structure agnostic framework for porting volatile index structures to persistent memory. TIPS provides a novel logging framework to provide efficient crash-consistent updates while also providing durable linearizability for concurrent indexing structures. The authors demonstrate that TIPS is able to provide 3 to 10 times higher performance than prior persistent memory optimized structures while providing strong consistency guarantees. TIPS demonstrates that it's a great idea to help aid developers in porting volatile indices to persistent memory rather than writing new indices from scratch, as a lot of effort has gone into optimizing volatile indices, and many of these optimizations can still be effectively leveraged in persistent memory. As we've seen, modern non-volatile memory devices have created renewed and invigorated research efforts in the field of persistent memory, and there are a lot of fascinating ways that persistent memory can be leveraged in today's high-performance systems. Here is an overview of all the papers in both ATC and OSDI which are related to persistent memory. If you're interested in persistent memory, please keep your eye out for any of these 6 papers in these 3 different sessions in both this year's annual technical conference and in OSDI.